In lesson 4.4, we're going to continue looking at exponential function problems where the inputs to those functions don't have to be whole numbers, they can be fractions and decimals. Specifically in problem 4.2, we are looking at population, where we're going to be doing something a little bit differently than what we usually do, which is we are going to model our equation with the input being how many decades it has been instead of how many years it has been. So let's look at the information they give us, because they want us to write an equation that tells us the population as a function of how many decades it has been since 1990. So they tell us, first of all, in 1990, the population was 95.3 million. So that's kind of our starting point, which means I know from the problems we looked at before that 95.3 is going to be that number that I begin with. That's my starting value. And then they also tell us that over the next decade, the population goes up, and specifically it goes up by 28.4%. Now we've looked at this before. If I want to find my growth factor, I can do 1 plus that growth rate there. So that's going to be 0.284. Or in other words, my growth factor is 1.284. So we're going to take each decade, we're going to multiply this 95.3 times 1.284. So if it's been, 10 years or 1 decade, we'll plug in a 1 for D. If it's been 30 years, which would be 3 decades, we'll plug in a 3. Problem 2 asks us to now write an expression to represent the population in 1996. So this is a little tricky because 1996 is not 1 decade later or 2 decades later. It's a fraction of a decade. But this is specifically 6 years have passed. And there are 10 years in a decade. So this is 0.6 decades. And we can do that. That's a perfectly fine calculation to make. This just means we're going to plug in 0.6 into our equation instead of plugging in like 0 or 1 or 2. So it's not going to be a whole number, but that is perfectly fine. So my expression is going to be 95.3 times 1.284, and the exponent is going to be 0.6. Now, I do want to point out you could technically also put 6/10. That's also fine. I'm just going to put the decimal here because we already found what it was. But you can also use a fraction. Changing gears a little bit, we're now trying to think about, well, what happens each year. So a student says the population of Nigeria grows at a rate of 2.84% every year. Now, they already tell us that this is incorrect. This is not true. And let's try to prove why that is not true. Let's use our equation still. So 1 year out of the 10 years that are in a decade is going to be 0.1 decades. I should probably add that up here. That's what the units are in this as well. Decades. So we can use this to figure out, well, what do we multiply by after 1 year? So we can go ahead and we can take that 1.284 and raise that to the 0.1 or the 1/10 exponent. And we can put that into our calculator, 1.284 with an exponent of 0.1, and that's going to give us 1.025. So here's the thing. This we can turn into a growth rate, right? This is our growth factor, and I can split that up. 1.025 can split up into 1 plus 0.025. So there is our actual growth rate, 0.025, not 2.84, because this is only 2.5% each year. Which we actually just answered the second part of this, which is to find the correct annual growth rate. So that's what we did right here. It's 2.5% each year, which shows that it is not 2.84% each year. There are other ways that you can show that 2.84% is wrong. For example, if you do 2.84 with an exponent of 10 for a decade, you will see that that does not give you the 28.4% that it should be. It gives you a bigger number. So there's our result, but there are other ways you can do this problem.